Okay, welcome to our Petroleum Engineering Department event for our incoming class of Fall 2020. My name is Melissa Dean, and we're very excited to speak with you today. Today, I have Dr. Fred Thurber, who is the program advisor for our Petroleum Engineering program. He is been in this industry, been a professor for many years, and is such a great professor to learn from. Y'all still have a great person to ask any and all questions when it comes to curriculum, what to expect in industry, what to expect at LSU. So please feel free to ask any and all questions during this event today. If you have any questions for me, I will be monitoring the chat function. And also my email is mhart3@lsu.edu if you have questions after this event. So with that, Fred Thurber, the floor is yours.
Thank you. Welcome, everyone. My name, again, is Dr. Fred Thurber. I'm with LSU's Kraft and Hawkins Department of Petroleum Engineering. I've been with the department for about 24 years now. I came from industry. I've worked, I started out working as a roughneck in the swamps and the marshes of Louisiana for Mallard Well Service. I've worked for Pennzoil. I've worked for Superior Oil Company. We were bought out by Mobil Oil Company, which was actually bought out by Exxon, then became ExxonMobil. So you might be familiar. Anyway, one thing I can tell you about our department is we have a number of people who have real life experience, who have worked in industry. And what I'd like to do is share my screen with you, and we can take a look at this department. A few things I'd like to pass on to you. Well, first of all, I know some of you coming in, it's really hard to make a decision. What type of career do you want to have? After all, many of you are what, 17, 18, 19, 20, 21 years old, and you're trying to pick a career for the rest of your life. And so you might be asking, why petroleum? Well, outside of the fact that if you want to do engineering and you really like the aspect of working with geology, working with the subsurface, you might be asking, why petroleum from a financial perspective? Or what's important about petroleum? Do we really need it? As we move forward, you're seeing what, Tesla's coming out with electric automobiles, and we're seeing energy saving devices. So why petroleum? Why would you want to come into petroleum? Well, first of all, I guess to answer that question, we have to first look and try to understand what are the variables that move the price of oil. Why does oil go up or down in price? And these are the variables that I list. In fact, a student in the introductory class, Petty 1010, a course that I teach, you do have to learn these variables. And if you talk to any economist, the economist will tell you really everything moves up or down based upon supply and demand. Well, if you look at the variables I have listed, I say that as well. Those are the number 1 and 2, only I reverse them. I think consumption or demand is as important as anything. Demand. Let's look at consumption right here. And if we go down and we look at world consumption, in 1985, this world used about 60 million barrels of oil per day. By 2019, the world used just over 100 million barrels of oil per day. The demand is great for petroleum. Not right now. We've had a downturn because of COVID-19, shutting down the economies of not just the United States, but other countries throughout the world. But if you look at it, the need for petroleum has only gone up. Well, some of you may be saying, well, what about Tesla? What about these electric cars that are coming out? Yes, that will reduce demand some, but think about it. What is petroleum actually used for? Look at the plastics you have in your house today. Those plastics are there because of petroleum. everything from fertilizers to toothpaste. There's probably nothing you're wearing that wasn't made without the help of the petrochemical process. It's quite amazing. And why have the numbers gone up as we see here, though? Uh, well, a couple reasons. One is the world's becoming a more densely populated place. The population of the world's increasing. But probably even more important than that is look at third and fourth world nations. We're a small world. I made a telephone call a few months ago to someone who was in Russia, who was in a little bitty community, no big city, not even close to Moscow. And yet I got through to them on a cell phone. And it's quite amazing. We're a smaller world. And because of that smaller world, energy is important. If you look at China, for example, China in 1970, the story goes, it was a much like North Korea is today. If you flew over it at night, the only lights you would see would be surface to air missiles headed your way. But since then, China has adopted capitalism. There are no democracy like our own, that's for sure, but they have adopted capitalism and they have grown because of it. Today, China has over 177 cities with over 1 million people. The demand from China for petroleum is great and it's expanding. We could say the same thing about India, another huge country from the population standard. But also, what about other third and fourth world nations? Without enough energy, without enough of the raw material to build the products that we use today, third and fourth world nations don't have a chance. So I believe this is a wonderful career path as you move forward. And we'll talk a little bit more on that as we move forward. The second one's production. Well, you know, some people thought, well, maybe we're just running out of oil because we've produced it all. But if you look at U.S. crude production, this is from 1940 to 1990. But if you look at it, I mean, actually from the beginning of time, that first well, all the way up, it was increasing up until 1970, when we hit a record in the United States of 9.64 million barrels of oil per day. Now, if you look, we started to slide. However, that slide was decreased and you saw two little small humps or level hump right here. What happened is the price of oil at this point was very high and a lot of people were investing in finding new sources of oil. We had in the early 70s the Arab Oil Embargo. The price of gasoline doubled in a very short period of time, almost overnight. And then we started seeing a decrease in production in the 80s, mid 80s, and we saw that decrease up until, about 2008. And in 2008, we start to see an increase, a rapid increase. In fact, in 2009, we were producing 12.23 million barrels of oil per day, a new record for the United States. Why were we doing this? We were doing this because we have engineers to produce oil. You got to realize the first well that was drilled in Pennsylvania, and it was actually drilled by a blacksmith, and his boss, the head engineer in the job, was a person who actually got the job because he could ride the rails for free. He was a retired railroad conductor, Colonel Drake. Pretty interesting. Well, now it takes a lot of scientific knowledge and engineering knowledge to be able to drill these complex wells. We found a way to drill and produce from a rock called shale, S-H-A-L-E. Okay. What makes shale different than a conventional reservoir rock? You see, up until about 2008, we were producing predominantly from a conventional reservoir, which would be sandstone, limestone, or dolomite, because those rocks are porous and they're permeable. Fluid can flow from one side to the other, much like fluid can flow through a sponge. Shale if you want a picture of what shale looks like, that all shales are different, but it's much like mud, silt and clay particles. And while there's pore space where oil can reside, there's no ability, the pore space is not connected, and oil cannot flow from one side to the other. So we had to develop techniques. That's a real interesting story. A lot of people wonder, well, how did that happen? It happened over a long period of time. I think Jimmy Carter was president in the mid 1970s, and the U.S. was investing lots of money. In fact, many people were complaining that the U.S. was investing about $130 million in the Shale Eastern Gas Project in Pennsylvania and a couple smaller projects as well. Everyone knew that shales held oil, but even engineers and geologists in the industry at the time did not believe that you had any chance to actually produce commercially oil and gas. Okay. However, there was a man out of Texas, Mitchell. He owned Mitchell Energy, and he thought he had a field around the Dallas-Fort Worth area. And he thought that field was just prime for this new technology, this new technique. And so he teamed up with the federal government. The federal government helped him out, gave him all their knowledge. In fact, they even paid for the first well that was drilled horizontally. Wells typically are vertical. Well, this was vertical, then horizontal. And in 91, 92, that first well was paid for by the federal government because this was an extension of research. This was an excellent example of the government and industry working together to help all citizens of our country, in fact, of the world. So we start producing a lot more petroleum. Of course, there's a lot of others. Inventories are very important, and I'm going to tie inventories and spare production capacity and geopolitical risk together just to show you how these come into play when you're looking at the price of oil. This is the king of Saudi Arabia with Franklin Delano Roosevelt in 1945. And they were negotiating in the Suez Canal, negotiating a deal where the U.S. would provide protection so Saudi Arabia could sell its oil. The U.S. would keep the sea lanes open, and exchange that oil would flow to the U.S. and to our allies. And every president since Franklin Delano Roosevelt, be it Democrat or Republican, has pretty much honored this agreement, has worked with Saudi Arabia. Even though Saudi Arabia is definitely a different system than the system we have, there is a kingdom in Saudi Arabia, not a democracy. Well, what is oil? You know, we talk about oil and as if it were one particular product, but what you've got to remember, oil is hydrocarbons. Okay, but there's a lot of different types of hydrocarbon structures. So what is oil? Let's look at it. There are many different types of oil: crude oils, heavy oils, extra heavy oils, natural gas liquids, ultra deep oils, tar, oil sands or bitumens, a condensate from tight shale oils or oil shale, which is keratin. This is a picture just to give you an idea of how oils can look different. In fact, if you look at the first one that looks yellow, actually, I've opened up the spigot on a well before, and the oil that would come out was as clear as a glass of water. And you could actually run it in your automobile. I wouldn't advise it. The octane level was very low. It's called condensate that comes from a natural gas well. But it would run in your automobile. How do we measure oils? Well, the principal measurement, there's a number of measures you will learn when you go into the program. In fact, you will learn in the introductory program how we measure oil. But one of the majors is to measure the specific gravity of oil. Okay. And in the oil industry, we like to use a standard called API, American Petroleum Institute. They set the standard for the oil industry. And I think because engineers really don't like, petroleum engineers anyway, don't like to deal with fractions. You see, if the specific gravity of water is 1, so anything lighter than water, such as oil, would be less than 1. You'd be dealing with fractions. So we use this equation right here. Degrees API equals 141.5 divided by the specific gravity at standard temperature, standard pressure, because pressure and temperature can affect the density reading, minus 131.5. So if we were to look at water, for example, water would become what? 10. So that'd be 141.5 divided by 1, which is the specific gravity, minus 131.5. Anyway, let's move on. Natural gas liquids are really important in this country because we do produce a lot of shale today. We produce a lot of natural gas liquids. A lot of people consider natural gas to be methane, CH4, 1 carbon atom, 4 hydrogen atoms. But yet there are some heavier components to this as well. Ethane, propane, butane, isobutane, and pentanes. Let's move on. Well, I'll tell you what, I'm going to go back to this just for a second. Ethane, for example. Ethane is used to produce ethylene, which is used to produce plastics. In this country, today, we produce plastics for about 1/4 to 1/3 of the cost that Europe can produce plastics because of our shale production. And if you go back to the George Bush II administration, we were building liquefied natural gas facilities to import liquefied natural gas from other parts of the world. Today, we use facilities to export liquefied natural gas because we have so much. During the George Bush II administration, because our knowledge of producing from shale had not yet developed, we saw manufacturers, petrochemical manufacturing, leave these shores that we thought would never return again. But they have returned. During the Barack Obama administration, when shale production really took off, we saw these manufacturing facilities come back to our shores because we now can produce lots of natural gas and the natural gas liquids. I will put you in Petty 1010. First semester or second semester, you're here. Petty 1010 is an introductory class to help you decide if this is really your cup of tea, if this is really what you would like to do. Because a lot of students come into petroleum engineering because typically with the 24 years I've been here, all but maybe 4 or 5 years, petroleum engineers tend to have the highest starting salaries. But it takes more than that. If this is going to be your career path, it has to be something you develop a passion for, something you will like and you'll enjoy. What will students learn? Well, we go into current events. We start out the class usually with current events, sometimes past events, looking at history. We look at strengths, weaknesses, opportunities, and threats. We look at the good and the bad. Current events sometimes are positive toward the oil industry, sometimes they're negative, but we need to talk about that so you understand what this industry is all about. Of course, you're going to learn about geology and rock and fluid properties. Very important. You see, if I were a chemical engineer, I might be flowing gasoline through a 3-inch pipe. and I would know the properties of the gasoline. I would know the pressure and the temperature inside the pipe, the diameter of the pipe. I would know all of this. I could predict how much gasoline would go through at any period of time. But if you don't understand the geology, what you've got to realize is we're not flowing a single phase fluid. We're flowing a multi-phase fluid through a porous median. What I mean by that, it's not diesel, it's not 10W20 motor oil, it's not gasoline or natural gas or water. It's all of this and more, and we're flowing it through a rock that we might believe that the diameter changes. In fact, really, if you look at a cave, that's what the pore throats look like. So at one point of a cave, you might have 15 feet elevation. At another point, it's so small you can barely squeeze through if you're laying on your belly. And that's what the oil flows through pore space. We're going to teach you a lot about drilling. We drill in the deep waters of the Gulf of Mexico, where you might be in 10,000 feet of water before you start to drill a well. You might be drilling 25,000 feet deep into pressures of 600 degrees Fahrenheit. Temperatures of 600 degrees Fahrenheit, pressures of over 15,000 pounds per square inch. We're going to teach you how to look at a reservoir using sophisticated logging tools to analyze that well's potential to produce oil and gas. We're going to teach you about the production equipment that you need to use. When you bring the oil and gas to the surface, there are situations where you might be producing a well, and for every barrel of oil, 95% of that barrel is water. And you have to environmentally friendly dispose of that water. So we're going to teach you about production, all the variables that go into producing wells. We're going to talk about reservoir engineering. How does a reservoir engineer go about their job? A lot of people call them asset managers. Why are they asset managers? Because the asset of the oil company is the reservoir itself. So when we hit oil, if we drill and hit oil, now the question is to the reservoir engineer, how many wells do we need to drill to properly drain that reservoir? You got to realize a well could run you millions of dollars. So you don't want to drill more than you have to, but if you don't drill enough, you'll never produce the oil that's in the ground, and you'll leave lots of money behind, lots of profits behind. You'll learn a lot about that. We'll talk about petroleum land management. In this country, the government doesn't own all the land. And so it's a lot of private ownership. You have to learn all about the contracts, how to negotiate, to be able to drill on someone's land. We'll go into engineering ethics. I have some fantastic case studies where the oil industry did not do well. Major companies did not do well. It's not to say negative things about the major companies, but it's to teach you about their mistakes in the past so you don't make the same mistake. Understanding history is so important. Let's move on. In the classroom, petroleum engineering, there's a lot of hands-on learning. So this is one of our lab facilities. I don't think you'll find any other department with a facility quite like this. This is a multi-million-dollar lab. We have 6 wells on campus. The first one was actually drilled by an independent oil man, and it was a dry hole. So he gave it to LSU, gave it to our department. to be able to use for training purposes. We have since developed that well for training and added 5 additional wells for training. No one in North America has anything like this. In fact, one of the courses you will take is a course you take in your junior year called Blowout Prevention. If you go to any other school in the country, you will learn about blowout prevention by operating a simulator on a computer. Well, let me tell you, before you get to operate the real equipment here, you will operate a simulator here too as well. The difference is, though, we have all of the equipment as if you were really on a rig, and we will allow you to operate the real equipment. We do train industry out here as well. Quite a facility. We get so much support from industry. It is amazing. We are so blessed. This is the control room of the well facility blowout lab that you see. And these are students in here operating the equipment. This is at the facility as well. We have areas where we use for production lab experiments. And this is a typical situation where you'll have 4 or 5 students who work together to solve a problem, to work through an experiment, to understand the equipment that a production engineer has to be familiar with. Now, one thing I'd like to tell you, I hope all of you stay with petroleum engineering, but I don't know, regardless of where you go, whether you go to the art department or the history department, educational research has proven that students who participate in professional organizations outperform their peers academically and professionally. And there's no question about that. Plus, it's a lot of fun. For petroleum engineering, we have a number of student organizations. The biggest and the one that most students join is the Society of Petroleum Engineers, the SPE. And everyone will want to join the SPE. Industry always picks up the tab. So there's actually no cost. I think Chevron picked up the tab last year and probably will do so this year. We also have the American Association of Drilling Engineers, AADE. If you believe that you really are interested in the drilling aspect of petroleum engineering, you might want to join the American Association of Drilling Engineers. Now, many of you will really not know if this is going to be an area you'll find extremely interesting until you get further into the program. But we do have a lot of freshmen and sophomores in the AADE. And of course, we have all students in the SPE. Now, there is the SPWLA, Society of Petrophysicists and Well Log Analysts. Most students don't really join this until they get into their junior year. There's a sophomore class, the second semester of the sophomore year, that you'll take called well logging. And that's where I guess you'll develop the interest in this course. So this is a much smaller organization, but a very good organization. If this is something you're very interested in, petrophysicists are in high demand usually, and salaries are pretty good for them. Then there is the American Rock Mechanics Association. These are people who look at shales and try to understand shales, because as an industry representative told me, we're producing a lot of oil, he said, from shale in this country, but we don't begin to understand shales. Our knowledge has a long way to go to understand shale production. Anyway, bottom line is, I don't care what you do in life, join these professional organizations, whatever you go into. I hope it's petroleum. If it's petroleum, we're very rich and we're very blessed because these organizations are a big help. This, just to give you an idea, this is a group of SPE members who are in Denver, Colorado at the SPE National Convention. In fact, if it would not be for COVID-19, this was from a few years back, and I pulled this picture in over some of the later pictures because we would have been in Denver again this year with probably a substantially larger group than what you see here. But the SPE always has a golf tournament every year where industry pays to play with our students. It helps the students raise money for events and activities that they have, and it gives the industry a chance to get to know our students, get to meet our students. If you don't play golf, it doesn't matter. The way they play is the type of game where as long as there's one person out of four who can hit a golf ball, you're going to be okay. You play as a team. Let's see. Okay, student outcomes. I'm just going to briefly read through these really fast because student outcomes are very important. One thing we focus on are our outcomes. What is our goal? What do we want to help what do we want when people graduate from here? We want you to have the ability to identify, formulate, and solve complex engineering problems by applying principles of engineering, science, and mathematics. We want you to have an ability to apply engineering, design, and to produce solutions that meet specific needs to consider public health, safety, and welfare, as well as global, cultural, societal, or social, and environmental and economic factors. We want you to have an ability to communicate effectively with a range of audiences. If an engineer doesn't have good communication skills, he or she is not going to be successful. And it's not just being able to be a good public speaker. We'll talk a lot about that, beginning with Petty 1010, but you'll get pieces of communication throughout the whole curriculum. You want the student or the graduate to have an ability to recognize ethical and professional responsibilities in engineering situations and make informed judgments which must consider the impact of engineering solutions in global, economic, environmental, societal contexts. We also want this graduate to have an ability to function effectively on a team whose members together provide leadership, create collaborative and inclusive environment, establish goals, plan tasks, and meet objectives. Working as a team member is extremely important. There's no one who knows it all. You are only as good as the team. Good example was last year. We had a fantastic quarterback at LSU, but it was the whole team that gave us the national championship. And last, an ability to develop and conduct appropriate experimentation, analyze and interpret data, and use engineering judgment to draw conclusions. In other words, you don't want to act like a Democrat. You don't want to act like a Republican. Those are parties. That's a passion. Engineers look at data and let data guide them in making decisions. So important. I said, well, what really separates petroleum engineering from other engineering disciplines? And geology. You have to understand the subsurface. So yes, you do take geology courses. And we just moved through here. I talked about a little bit earlier, conventional reservoirs where the oil would flow from one pore to the other. That's a conventional reservoir. In shale reservoirs, these pore spaces are not connected. A little bit different. We talked about well logging or formation evaluation, becoming a petrophysicist, a type of petroleum engineer. This is where we run sophisticated tools down on a wire line, and as we pull them up, we start taking measurements. And I'm going to show you something in a moment, so we won't go into depth on what this is. We have to understand the reservoir itself. Does the reservoir have oil in it with dissolved gas? Is it oil with gas that is separated from the reservoir? Or is it a combination of both? This would be like a Coca-Cola, would it not? If you pop the top, there's gas that escapes, but there also is gas dissolved in that Coca-Cola. Now, naturally, it's not a hydrocarbon, it's carbon dioxide in Coca-Cola, but there is gas. And if you leave that Coca-Cola, open it up, and then leave it on the counter and forget about it, and come back the next day and you try to drink it, it's going to be flat. The gas will be gone. And so you have to understand the reservoir, because all of this depends on how you're going to produce it. Worldwide, we leave about 64% of oil in the ground. When I first came here, it was about 70% left in the ground. So we're improving. But every reservoir is different. Reservoir engineering is quite interesting. Sometimes we drill one well to produce oil, and you see on this well, we have a pump that will pump the oil out of the ground. Some wells flow on their own. You don't need a pump, but you also see 4 additional wells in order to inject water or some type of chemicals, such as surfactants, soaps, to be able to produce more oil from the reservoir. Real interesting. And if you look at this rig, just to give you an idea of what type of operation this is. In fact, if you look at the derrick, the area that's going up, and you look at the dark things in the derrick right here, this is drill pipe. This drill pipe is about 90 feet high, and at the bottom, that's the floor of where everything happens, where the drilling crew, the roughnecks, and the driller, not the drilling engineer, but the driller, put the pipe in the hole and take it out and drill the well. If you notice, there's a helicopter here sitting on a heliport. You've got 3 cranes. You've got an area to flare natural gas. Quite a setup. Now, what I'd like to do, though, real fast, is I'd like to kind of go through our program. Let's see if I'm staying on schedule. Okay.
We got a few more minutes, Dr. Thurber.
A few more minutes. Okay. Okay. Here's what we've got. Here's our program. If you look at it, in fact, let me do it this way. Okay. Pardon me one moment while we get this kicked off. There we go. Okay, boom. Anyway, let's go here and here. This is Petty 1010 right here. This is the introductory class. We'd like you to take that either the first or second semester you're here, because the worst thing you can do is go through a curriculum and then realize, well, maybe you're a straight A student and you never get burned, but that doesn't mean you really enjoy the work you're doing. And so we like you to give you that understanding of what this course is all about, what this curriculum is all about early. Plus, it gives you a rudimentary understanding of all the material so you can move forward through the curriculum. We do require Math 1550 and Math 1552. That's Calculus 1 and Calculus 2. If you need to take algebra or trigonometry, it's available to you, but it does not count in the 128 credit hours toward the curriculum. So please be aware of that. So we have 9 hours of calculus, 3 hours of differential equations, and that's all the math you have in this curriculum. Pretty nice, isn't it? Look, everything you deal with in engineering, all your courses deal with math. So the difference is you're using it. It's engineering math. Engineering math is easy math. Why is it easy? It's because you're solving a particular problem. It's not theoretical math. Okay. Physics. There are 3 physics courses: particle mechanics, fields, electricity, magnetism, and then there's thermal and waves. And all the math courses, I take it back, in the first 2 math courses, the first 2 calculus courses, and the 3 physics courses, as well as rock properties right here, petroleum engineering rock properties, and statics, which is the first of the engineering science courses, you must earn a C grade or better. In order to be, see, students come in under the center for the freshman year, right? That means you're going to have counselors who are excellent at working with freshmen. Freshmen have problems that juniors and seniors do not. Sophomores, juniors, and seniors do not. But yet, the goal is to go into your college. To be in the College of Engineering, you have to meet all the requirements of the College of Engineering, 24 credit hours with a 2.0 GPA or higher, but you also must have a minimum 2.8 GPA on all the courses that apply to petroleum engineering. So your average has to be a 2.8 GPA in order to be accepted into petroleum engineering. If you don't meet the requirement the first time, yes, you can stay in the curriculum, continue to pursue it, but you must meet the 2.8 minimum to be in the College of Engineering as a petroleum engineering major. Now, let's say you're not an A student, but you're not a DF student either, and you really believe this is your path and you would like to graduate as a petroleum engineer, but you don't have the 2.8 GPA, you can petition the department. And if we believe you will honestly get through this program, and this is what you would like to do, maybe you're a member of the Society of Petroleum Engineers, you're very active, maybe you have summer internship or so, yes, we'll probably accept you into the program. We just want to be sure that you're staying with this program for the right reasons. We want you to succeed. The introductory class, some people put introductory classes as gatekeepers. This is not a gatekeeper. I teach it. I know. Don't misunderstand me. There will be students who will make an F in that class every semester because maybe they go to the bars at 2 o'clock in the morning routinely. Well, but if you put forth the effort, you're going to get through the class and probably earn a good grade. But the purpose of that class is to help you understand if this is what you would like to continue to do. Let's see now. I'm going to show you one other thing real quick. Whoops, let's go back to this. I'm going to go right here. I'm going to go and give you, you know what? Let's see if I can do this real quick. There we go. Just erase that so we don't have a problem. I'm going to give you an example of, there we go. Okay. Okay, I'm going to give you an example of a problem that you might have to work as a petroleum engineer. So just to give you an idea, let me click it right here. What if someone comes into your office after you've graduated? Maybe you've been working for 5 years. Maybe it was a classmate. In fact, a friend with whom you've graduated from LSU's Crafty and Hawkins Department of Petroleum Engineering. And he or she wants you to invest with them. And they believe they have a very large oil field, but they need money to develop that oil field. And so they're offering you a wonderful opportunity. That's not unheard of. That's not uncommon. And they want you to invest $100,000. The reservoir covers 68.87 acres, the person tells you. So we know that 1 acre equals 43,560 square feet. So if it's 68, it's roughly about 3,000 square feet. So the first question you would ask is, well, how much oil is in the reservoir? But that's a complex question. How do we know that? Well, we have to go through a calculation. And these are the calculations we go through. We take the area in square feet, we multiply it by the reservoir thickness. How thick is the reservoir? And let's just move on through that a little bit faster. So here's what we calculate. The reservoir thickness, this tells us that we're calculating original oil in place. And we know our areal extent is 3 million square feet. And the reservoir thickness is 25 feet thick. We would learn that from a well log, how thick it is. You would have to tell me that, in fact, in Petty 1010 by looking at the reservoir. So we would multiply 3 million by 25 feet. And that would give us 75 million cubic feet. But that's not oil. That's just telling us how big the reservoir is. And so what we do is we look at something like this. I'm not going to spend a lot of time with this, but these are well logs. Well logs, what are they? Sophisticated tools that we send down into the well, and as we pull it up to the surface, we take measurements. What type of measurements? Well, this is called the spontaneous potential. It's an electrical current that forms naturally. Why does it form naturally? Because if this is the well right here, as we drill a well, we have to fill the well with fluid. Starts out, it might be water, but it actually becomes muddy water real soon. In fact, what it's called is drilling mud or drilling fluid. In fact, we have a laboratory class that you take in your senior year on drilling fluids, because drilling fluids can cost over $2 million on a well. And anyway, these drilling fluids that are in the well, as we drill through the formation, they commingle with the fluid that's in the reservoir, because the fluids have different densities, different salinities. There's an ionic exchange that takes place, which forms an electrical current. And by looking at this electrical current, we can determine if we're in a reservoir rock or not. We also shoot electricity into the formation and measure the resistance to the flow of electricity. Because if we're in water or salt water, which is what you find in South Louisiana below 2,500 feet, we know there's very little resistance to the flow of electricity. That's why you don't touch an electric plug if your hands are wet, right? But if it's oil or natural gas, there's a lot of resistance to the flow of electricity. So by looking at that curve, I can tell if there's oil there or not. There's sound waves that we shoot into the formation which helps us measure how much pore space is in the rock. If that rock is comprised of 1/3 pore space, there's a lot more oil there than if it's 1/5 pore space, right? That would make sense. We measure the natural gamma radiation of the earth. That can tell us what type of rock we're in. We shoot neutrons into the formation or high-speed gamma rays into the formation. That can also tell us how much pore space there is in the rock. It can also point out if there's natural gas in the rock or if it's a liquid. And if it's a liquid, we can look at the resistivity and tell us what kind of liquid. So I just want to point that out really quick. So this is how we would solve this problem. We would, the next thing we would multiply would be for our answer is we multiply by porosity. And this is the equation you will learn in Petty 1010 to calculate porosity. How much pore space is there? And then we would go back to the rock and we would look at oil saturation. Well, how much of that liquid that's in the pore space is actually oil? Or how much is water? So what we do is we calculate that. You will learn how to do that in Petty 1010 as well. And we calculate it for this well. There's 81% oil. And so let's go on down just a little bit again. So the next thing we do is we know the answer will give us an answer in cubic feet, but oil's measured in barrels. So we take our answer and divide it by 5.614, which will convert cubic feet to barrel. And we find that we have 3,246,348 barrels in the ground. That's a good estimate. For the class, I require students to round off to the nearest whole barrel. In reality, we wouldn't even count the 348 barrels. In fact, we'd probably round this off to 3,250,000 barrels. But that's original oil in place. That doesn't mean we can get it out of the ground, because we leave most of the oil in the ground on the average. So how many can we pull out of the ground? And you learn about reservoir. We go into reservoirs at this point, which we don't have time to do today, but we'll look at the reservoir to try to get an understanding of how much might we pull out, because we want to look at the reservoir pressures, the geology involved, and look at the history of similar wells. And we say on this one, we can pull out about 75%. So that means we have actually 2,434,761 barrels that we can bring to the surface. Correct? No, not quite yet. You see, a lot of oil has dissolved gas in it. And so we have to take an effect of the dissolved gas, because typically when we pull oil to the surface, the pressure decreases. The pressure in the reservoir of mine, gosh, it might be 1,500 pounds per square inch. And we bring it to the surface at what, 14.7 pounds per square inch? What happens as we pull it up to the surface? We hit the bubble point. That's, remember chemistry in 8th grade, right? That's the point at which the gas that's dissolved in the liquid begins to separate, and the gas separates. So when you get that barrel of oil to the surface, you have some gas and some oil, but you'll have less than a barrel of oil. So you will learn, of course, how to calculate that number. We call it B sub O. In this example, we used 1.1 for our B sub O calculation. So instead of producing and selling 2,434,761 barrels, will produce and sell 2,213,419 barrels of oil, stock tank barrels. So I just want to pull that up for just a moment. I thought you would find that quite interesting. I guess at this point, I'm going to open the floor for any questions that you might have regarding the petroleum engineering profession, regarding our program, our curriculum, anything you have.
Students, feel free, since it's a small group, you can use your microphones today if you would like. We do have a question though. Do you expect petroleum engineering jobs to open up in the next 10 years, like to still be in existence?
Look, I believe it will be a good career path for anybody moving forward. And this is a simple reason, okay? If you looked originally when we talked about how petroleum moved up and the world used in 2019 over 100 million barrels of oil per day, that number has decreased, but so has that number decreased for just about anything we use today, as we've been in lockdown, economies haven't been back up to normal. The estimates from the the International Energy Institute are that we will see a return to over 100 million barrels per day beginning 2021. Oh, of course, that's an estimate. We'll have to see if that's true. But in the long term, when you're looking long term, yes, I do see jobs are going to be available for a number of reasons. If you look at, well, let me go to this really, really quick. And let's see if I can, yeah, if you look at this, when you look here, right here, if you go through this time, I came to work, in late 90s, mid 90s or so down here. And we were producing less and less oil. And there really were not a whole lot of students. But if you remember, the price of oil got very expensive. It got so expensive, people were paying actually, through most of the country, they were paying $4 or better per gallon. Even in even in Louisiana, we were seeing $4 at some stations, very high. And so what happened is shale production kicked in. It looked very promising. And there were a lot of students that decided to come into petroleum engineering, actually more than should have come into petroleum engineering. Our numbers got very, very high for a period of time. That bubble has pretty much worked its way through the system now. I've been here 24 years. I would say other than about 7 of those years, maybe 6 of those years, students who were graduating in May had a job by the end of May. I mean, before they graduated. And the exceptions to that would be the student who was very, very weak. And even that student would have a job by August. I see us returning to that. Our program is a much smaller program. It's not just LSU, it's all of the major universities who have petroleum engineering. You've got to remember, not all universities have petroleum engineering. Every university has an engineering program. For the most part, has probably either civil or mechanical, electrical, industrial, some of the major engineering areas. Petroleum is very limited. And because of that, there's going to be a shortage for engineers, for petroleum engineers, I believe, as we move forward. If you would graduate last May, yeah, it would have been tough to find a job. The price of oil was down. The need for petroleum was way down. Of course, a lot of career paths were in the same boat as petroleum in that respect. And our numbers from the larger class, when students came in, when oil prices were high, the classes were relatively large. Those large classes are gone. And so, yeah, I think it's a good career path. I really believe that. But again, you have to make that decision. That introductory class we have is very good at helping you. The current events, students tend to love the current events that we start out with because it talks about the good, the bad, and the ugly. So you can make your mind up whether this is really your cup of tea or not.
Awesome. Okay, any last questions before we wrap up? Are we all good?
Well, look, if there's no more questions, I sure look forward to seeing you in class. Those of you who are in the Petty 1010 class, you will see me. I'll be teaching that class again, and I look forward to seeing you.
Awesome. Thank you again, Dr. Thurber, for being available today. What is repeat your email address again, so if they have any questions before the start of the semester, they can reach out to you.
Okay, my email address is fthurbe@lsu.edu. If you send me an email and it doesn't go through, it's probably because you know my name is Thurber, but there is no R on my email. FTHURBE@lsu.edu.
Thank you again, Dr. Thurber. And if y'all need me for anything, my email is mhart3@lsu.edu. We look forward to seeing you in about a month. So if you have any questions, any concerns, or anything that you need prior to the semester, feel free to reach out to us. Again, thank y'all for joining. And as always, go engineering and go Tigers.